Today we're going to talk about two different ways that we can evaluate limits. And I'm going to start by looking at problem number 8 on page 50. This is a linear equation, and we're asked to evaluate the limit as x approaches 2. So for this particular problem, if it's a polynomial or another function where I can just take this value and plug it in and get an answer, then that's what I'm going to use. I'm going to use direct substitution to find this limit. So the limit here, I plug in 2, and negative 10 plus 23 happens to be 13. So the limit as x approaches 2 is 13. Here's another example. This function is a rational function, and we're asked to find the limit as x approaches 4. And again, we can go ahead and just use direct substitution, even though it's a rational function, because when I plug in 4 in for x, then I actually get an answer. It's not an indeterminate form. So I can just go ahead and evaluate that. The numerator is 5, and the denominator is 16 plus 12, which is 28, plus 2, which is 30. So my final answer is 1/6. The next problem we're going to look at is number 12, and this is also a rational function, but for this particular problem, if we try to evaluate the limit by direct substitution, what we will notice here is that we get an indeterminate form. Oops. So the top 25 plus 15 is 40 minus 40 is 0. And the denominator 5 minus 5 is also 0. And 0 over 0 is an indeterminate form. There are many other indeterminate forms that we're going to learn as we go through this class. So if we come across an indeterminate form, what we need to do is factor the numerator and see if we can somehow simplify, because we have a hole in our graph and we need to eliminate that in order to evaluate this limit. So the limit as x approaches 5 of this rational function will be the same as the limit as x approaches 5 for the simplified equation. And let me just set this up. Okay, so x squared is x times x, and then numbers that multiply to negative 40 and add up to 3 must be positive 8 and negative 5. And now I can eliminate the factors that match, that are creating the indeterminate form, and that are creating the hole on the graph. Now I can take what's left and I can use direct substitution. So if I plug in 5, the limit is 13. We're also going to look at number 14. This is a rational function, and if we try to evaluate the limit as x approaches 3, we're going to have a numerator of 27 plus 9, which is 36, and minus 15 and minus 21, which is also subtracting 36, so we get 0 on top, and 3 minus 3 in our denominator is also 0. So we're going to have to somehow simplify this equation. The problem I notice here is if I try to factor by grouping here and here, I can take out an x squared, it'll leave me with x plus 1, but I can't take anything out. What's left in parentheses won't match, so that's not really going to be useful. So I have to find another way to simplify, and I'm going to use synthetic division. So I'm going to look at my denominator here, and since I will be dividing by x minus 3, that equals 0 at positive 3. And then if I look at this equation in the numerator, I'm going to take all the coefficients of all of my terms. I have 1x cubed, I have 1x squared, negative 5x, and negative 21. And my process for dividing these is drop down the 1, multiply that by the 3, and write it in the next column, and then add that column. Multiply the 4 by the 3, put it in the next column, add those together. Multiply the 7 by the 3, write it in the next column, and add those together. And if this actually has a remainder of 0, then it tells me how the original equation factored. So now this equation here factors as my divisor was x, well, it has a 3 here, so it's x minus 3 times all of these coefficients, and it started out as 1x cubed, so this is a degree less, it's 1x squared. So I have x squared plus 4x plus 7. And now it's just like number 12. I can cancel the factor that creates a whole, and then I can use direct substitution and evaluate the limit. So my limit here is 9 plus 12 plus 7, which is 28.